I'm just going to let this thing keep recording. Okay. So everybody remember how to use a volumetric pipette?
Yes.
With the bulb and all that stuff. Okay. We won't have to go over that. All right. So you're going to have your data. It's going to be pH versus added base. So for 0 added base, you're going to get a pH somewhere in the neighborhood of like maybe 2.5, something like that. And then as you add base, your pH is going to increase, like 3, 4, something, all like that. So you get that data set. Then you plot it. So this is added base. This is your pH. And your pH is probably going to be in the neighborhood of around 2. Right? And it's going to go up quick to begin with, and then it's going to flatten out. Maybe more than that. Right? So your pH is going to start off increasing fast, and then it's going to slow down. And you're going to get this part of your curve. That's the buffer region right here, because the pH is not changing much. And then once you've exceeded your buffer, it's going to go like that. Flatten out at the top. Okay? This is going to be in milliliters. And what you're going to have here is your equivalence point. So at this point, and we don't need an indicator because we have a pH meter. Okay? So we're going to know exactly how much base, however much base it takes to reach the equivalence point. So where is the middle of the buffer range? 1/2 of that value. 1/2 of the amount of base added gives you the middle of the buffer range. Okay, so how do I know that? Well, you'll see it, but I know it because of Henderson-Hasselbalch. Oops. Okay. I know the best buffer range is where this one is equal to that one. Okay. So if I start off with this much, and I add base to it, and we end up with water plus this one, okay? Then at what point does this one equal that one? If you start off with this one, right, so much of that one, and this one is 0, then when are they equal? When you've used up half of this one, right? If you use up half of this one, minus a half x, and that gives you a plus half x over here, then this makes a half of your x here, half of your x there. Now they're equal, right? So if these two are equal, then that's the middle of your buffer zone. So half of your original amount of acid used up puts you right here. And how do we know that? Well, we've got this much to reach the equivalent point. That's when you've used all of that up. So you only want to use up half of it. So if we use up half of it, that puts us back at half the amount of base added. Okay? So now, with half the amount of base added, so let's just say this is, for argument's sake, 20 mils. So this would be 10 mils. So at 10 mils, you go up here, that's the middle of your buffer zone. Okay? We're not finished yet, because the question is, what's the Ka of acetic acid? Well, look, Anderson-Hasselbalch again. If we're in that buffer zone where this is equal to that, what is this term equal to? If that's equal to that, that's 1. Right? If that's equal to that, this term is equal to 1. And what's the log of 1? 0. 10 to the 0 power is 1. So that means this one drops out. And at that point, pH is equal to pKa. So you just have to read across here. That pH is pKa. Okay? And then all you have to do is take the anti-log of the negative. So you say 10 to the negative pKa is equal to your Ka. Okay? That's it. Simple. Real simple. And you figure out what this is and compare it to, this is your accepted value. 1.8 times 10 to the minus 5 is the accepted Ka of acetic acid. And you compare yours to that one. And say, what's your percent error? That's basically it. And then there's some discussion questions in here. Pre-lab questions. Let's see. Am I expecting the pre-lab? Let me see. Wait a minute. Let me look at your copy, the student copy. Lab questions, yes, there they are.
Yeah, we have discussion questions, pre-lab questions, and lab questions.
Are the pre-lab?
Pre-labs.
Yeah, there's, wait a minute.
There's 2 pre-labs,
Wait a minute.
3 discussions.
Let me look at your copy because I want to see what you're responsible for. I want to grade you on something I didn't give you to do. That would not be fair. There's discussion questions, all right. I'm supposed to work these with you before class. Pre-lab assigned students. All right. Well, I can give you some hints. How about that? Oops, too many copies. All right, let's work pre-labs first. I'm gonna leave that there until I figure out what pre-labs. Pre-labs. Which way did it go? Let's discussion. Pre-lab. Okay. We can erase the left-hand side pretty easy without disturbing the rest of it, in case we need it. So these are the pre-labs. First one. Write the balanced molecular equation for the titration of acetic acid with sodium hydroxide. The molecular equation, right? So if you're starting out with acetic acid, you're going to react it with what? Sodium hydroxide, right? So these are the 2 reactants. There. This is the molecular equation. So we're not going to bust it up into pieces. We're just going to say what happens. Well, this one, the hydroxyl separates and combines with the hydrogen, right? Makes water. H2O. What's left over? Well, sodium then combines with acetate, right? Let's see, this is an aqueous solution. This is aqueous. That's pure liquid. And this is aqueous. So everything's soluble. It's just we represent the balanced equation as in molecular form, even though we know that they're really ions in solution. But the question was asking you for the molecular equation. Okay, any questions about that one? That's fairly simple. Whenever you're doing an acid-base titration, or any titration for that matter, you need a balanced equation to work from. You need to know what's going on in the solution. Hard to see from there?
I don't have my contacts in there.
Oh, all right.
I was rushing out of the house.
Come on down. Which one is that? Wheel of Fortune?
Yeah.
Or is that Let's Make a Deal? Wheel of Fortune?
I think it's Wheel of Fortune.
I think we all say about the same thing anyway.
Yeah, that's right. Okay, the second one, the Ka of formic acid. So here's formic acid. That's formic acid. Now, you don't even know that to answer the question. The Ka is 1.8 times 10 to the minus 4 for formic acid. So actually, this is the proton that is released from formic acid right here. Not that one, this one. Just a point of information. The Ka of lactic acid. Lactic acid is, no, that's acetic acid. Lactic acid is, I think it's that one. But the Ka for lactic acid, let's see, this is formic acid, this is lactic acid. There we go, that makes it easier. The Ka for lactic acid is 1.4 times 10 to the minus 4. So they're pretty close. Which acid is stronger? Well,
Formic?
Yep.
No, well,
The largest Ka, right? Remember what Ka means? It means one proton ends up on the product side along with the conjugate base. So the bigger this side means stronger, which means this value has to be larger. So the largest value is the stronger acid, right? Did you say formic?
Mhm.
Yeah, that's right.
okay.
That's right. So formic acid is the stronger. Now the next question is, what's the pKa of each acid? Well, we just take the negative log of each one. pKa here, pKa there. Let's see. This one turns out to be 3.74 for formic acid, and this one is 3.85. So the pKa's are like the pHs. The lower the number, the more acidic. So the pKa's, the lower the number, the stronger the acid. Right, so 3.74 is less than 385, makes this one stronger. It's a similar, really an artifact of the log transformation. Same as pH, right? Low pH is stronger acid. So low Ka is also stronger acid. Okay? Those are the pre-lab questions. Now, let's see. Laboratory questions. Define the following terms. Define the following terms. No, that's discussion questions. Lab questions are different.
We're on the very back page.
Very back page. There's discussion questions. Here we go. Discussion questions. Is that in your printed copy?
Yes.
All right. So this is really just the definitions. Define these terms. So what's the equivalence point? That's the point in a titration where the moles of acid equals the moles of base.
This is at the point where they're equal.
They're exactly equal. Yep. Oh, that was A. B is endpoint. What's the endpoint of a reaction of an acid-base titration? It's related to the equivalence point. The endpoint is an approximation of the equivalence point based on the color change of an indicator. Okay. How about Ka? What is Ka for your acid? It's the acid. It can either be protons or hydroniums, either one. Because these are the products, right? Products. And this is your undissociated acid. So that's what your Ka represents. It's the equilibrium constant for the dissociation of an acid. D, what is pKa equal to? It's simple. It's just a log transformation. It's a negative log of the Ka. That's it. Let's see. And there's two more. Discussion question 2. If you have 23.9 milliliters of sodium hydroxide solution, aqueous sodium hydroxide, and that much sodium hydroxide solution, and we don't know what the concentration is. Right. And we've got that titrated against 25 milliliters of 0.105 acetic acid. Let's see. What's my abbreviation for that? There. That's my abbreviation for acetic acid. Okay. Then the question is, what's the concentration of your sodium hydroxide? did this before, didn't we? First semester. When we were standardizing our base to determine the molecular weight of citric acid. Yeah, we had to do this one. So what we're saying is the molarity of the base times the volume of the base is equal to the molarity of the acid times the volume of the acid. That's only if there's one hydroxyl and one acetate for each one. That works. If you used sulfuric acid here or a polyprotic, that wouldn't work. You would have to substitute instead normality here. Okay. But we can use this one because they're 1 to 1. Okay, so the molarity of the base is our unknown. The volume is 23.9 milliliters. And that's equal to the molarity here, 105 and 25. Okay? So if we solve that for the molarity of the base, we should get in the neighborhood of 0.11 of those. Okay. So what would we do if we had a diprotic acid here? That's 2 protons. Well, the normality of the base would be the same, right? Because it's only got 1. But here, the normality of this acid would be twice, right? Because the molarity of the acid produces, in the first case, 1 proton, but in the second case, 2 protons. So the normality would be twice that. And then you could plug it into your expression. Hold on a second. Is that right? Let me see. Let's do that. That would be our diprotic acid. And if I said this was 0.1 molar, then it would produce 0.2 molar protons. Right, okay, so it's double the molarity. Yeah. I'm just checking myself. The normality. Actually, that's the molarity of the acid. No, normality would be this. Normal. Why? Because this then would produce 0.1 molar hydrogen. Okay, I said that backwards. If this were diprotic, the normality would be half that. 0.0525. That works. That's why I didn't spend a whole lot of time on normality, because it's useful if you use it a lot in your work. But if you don't, you can get confused real fast. So the best rule to follow is, rather than use normality, write out your balanced equation. Then you can use molarity on the components and use your conversion, like 2 to 1, 3 to 1, to determine the values for each side. Okay, 3. In a titration of weak acid, the midpoint corresponds to a pH value of 6.1. The midpoint? Oh, okay, so the midpoint, what we're saying is the midpoint of the reaction is where half of the acid is neutralized. That's right in the middle of the buffer zone. And that pH, in this case, is 6.1. That's what they mean by midpoint. What are the pKa and the P and the Ka? Well, if that's the midpoint, then this is equal to the pKa. And the Ka is equal to 10 to the minus 6.1. Or the anti-log of minus 6.1, which is 8 times 10 to the minus 7. Okay? That one is a problem in wording. When it says, what does it mean by the midpoint? We've not used the midpoint as a descriptive term. So you have to understand what midpoint means. Midpoint just means right here. That's the whole point, that's the midpoint. And then the rest of it is simple. Okay? So did I leave any? Yeah, I did leave some laboratory questions that need to be answered on your own. Well, let's see. Should we be expecting negative?
She said she was on her way, she just took her traffic.
Okay.
She don't live too far away though, so she should.
Okay. So we'll take a short break, reconvene in the lab. And everything's either set up on the bench or is on the table or rolling tray. Let's stop this thing before we get